My name is Giovanni, and I'm a PhD student in AI in Italy. And together with the people that I work with, we are pretty passionate about Julia. We have been using it for 3 years, and I'm pretty excited to be here to showcase our work. So essentially, I'm going to present this framework of our own creation for symbolic learning. The name of the framework is Sole. In this context, when I say symbolic learning, I mean that part of machine learning, that deals with models that are inherently based on formal logical languages. And the most commonly known example of such models is the decision tree. These models are especially interesting in contexts where the application of uninterpretable AI models raises ethical concerns. So these techniques, more specifically, can learn models that are transparent in nature and that you can understand how they get to given conclusions. So in order to explain this, I will consider a decision tree and a neural network for an example of a classification task. So I have a classification data set where each instance is a patient described, a patient in a hospital, described by a set of scalar values. And the task is that of classifying the patient as sick or healthy. So let's say I have trained a neural network for this task. When a new instance comes and I have to classify it, I input the information in the input layer, but then the input information kind of ends up permeating the whole structure of the network, so it gets really difficult to understand why the network gives a certain outcome. Instead, if we use a model such as a decision tree, the instance is essentially an object onto which we test certain conditions, and each test is either, each condition is either true or false on the instance. So the instance kind of travels compactly throughout the model so that you can tell exactly why a given classification was given. So this can be really interesting because you can really, you can extract classification rules such as this one. An expert, in this case, a doctor might look at this rule. They might learn, acquire new knowledge. They might modify the rule if it doesn't comply with certain medical standards. These kind of techniques have their own roots to the 80s, basically, with expert systems and with the famous CART decision tree learning algorithm. But they have been kind of overshadowed in the past 20 years because of the deep learning revolution. And today, it appears that they have been kind of relegated to the realm of tabular data. So the question is, what do you do when you have more complex data? When, for example, your patients are described as a multivariate time series, or, for example, as described by an image that is the scan of the brain. Well, what you do usually, what you would do if you want to use a decision tree, for example, in order to achieve interpretable modeling, is you extract feature representations of the image. So you basically represent an image via a set of scalar values, so that you can basically fit a data set of images into a tabular form. And then you can train a decision tree that makes decisions according to those computed values. For example, with an image, you could compute the minimum and maximum value for each of the color channels. You can even trade some simplicity of this model for higher performances if you use, instead of the minimum and maximum functions, more complex features, for example, features tailored for computer vision tasks. But the idea, our idea, would be that when you have this kind of data in your hand, instead of destroying it and simplifying it that much, you would like to perform some kind of spatial or temporal reasoning. For example, it would be nice to express some rule, some classification rule, such as that if in the image there exists a region with a lot of red color, partially overlapping with another region with another characteristics, such as the little green color, with an inner region with a lot of blue color, then this patient is sick. So, but in order to extract this kind of, and to perform this, to express this kind of reasoning, we need to take a step back and lay out the logical foundations of this flavor of symbolic learning. So we've built a set of packages, starting with a package for representing logical formulas and checking their truth on the logical interpretations. Then we built a package for representing non-tabular datasets. And finally, we have a package where we define what symbolic models are. This is the Sole framework. We are also working on other packages, for example, for post-hoc analysis of the extracted algorithms. And at the moment, the only learning algorithm is implemented in this package, which implements like a cart-like learning algorithm for that can natively perform spatial and temporal reasoning on this kind of data. So now I'm going to talk about the logical foundations and the core concepts behind Sole. And we'll start with a perhaps novel view on traditional symbolic learning. So the first point would be that decision trees, such as the one that I've showed earlier, are inherently based on the simplest logical formalism, which is propositional logic, which we probably all know. Given a set of propositions that represent facts that may be true or not, we can say that propositional logical formula comes from this grammar. So we can have formulas such as P, not Q, not P and Q. And these formulas can be checked on structures that we call logical interpretations, which sort of assign truth values to the propositions. At the propositional level, an interpretation is exactly a mapping from the set of propositions to values that are true or false. And we can define the truth of a formula, so we can say that a formula is true on a propositional interpretation via a set of very simple rules, so that we can say that, for example, this formula P is true on this interpretation because you have a true value for it, and this formula, not P and Q, is true on this interpretation. We follow this truth-checking algorithm. Okay, so in SoleLogics, basically, we have the concept of a proposition, which is essentially a wrapper around anything you want. It could be a string or an integer. In this case, I'm going to, so I have instantiated two propositions, P and Q, and I show that I can manually compose a formula. Then I can instantiate a propositional interpretation, assigning true to P and false to Q, and I can check the formula on the interpretation. Formulas can also be parsed from string or generated randomly. So this is like the most abstract layer of Sole. I haven't given a meaning to the propositions. You know, they're just names as far as I'm concerned. But in propositional symbolic learning, what you do is you interpret a tabular data set on a set of scalar variables. So, for example, the classification data set that I've showed earlier, as a set of logical interpretations, where the propositions are scalar conditions on the values of the variables. So let me go back. If you have a variable such as this one, for which you have numerical values, you can produce a set of propositions, and each instance in the dataset is actually, it holds a true or false value for that condition, right? So A decision tree then, such as this, is nothing else than sort of an if-else, a nested if-else structure that repeatedly tests the truth of these conditions on the instance. I can extend this and say that, in general, you could have formulas here, and that the functioning of this model is strictly tied to the definition of of truth of a formula on a given interpretation. So then I can define symbolic models with this in mind. In Sole, we have two basic blocks for symbolic modeling, which are symbolic models as well. The branch, which is sort of an if-then-else block. It outputs a given outcome if the input satisfies, so if a formula is true on the given input and a different outcome otherwise. And the rule, which is kind of the same, but it doesn't really have an answer in the negative case. So it looks like this. And I call the formulas to be checked antecedents and the possible outcomes, the consequence of these objects. So in Sole, for example, the branch, I can model it as an object that have an antecedent, two consequence, and an info structure holding additional information, such as the accuracy for this model, in the case that it was learned. If you look closely, the consequences are actually of the same type of these objects, abstract model. And this is because you can you can allow consequence to be other models, and you get more complex structures. What is a decision tree if not a nesting of branches? So yeah, we define the decision tree in this way. And once again, the semantics is pretty straightforward. In this case, you enumerate all of the root to leaf paths, and you check for the conjunction of all of the formulas that you find along the path. A decision list is another symbolic model. I don't know if I have the time for that. So I'll just keep on going. But yeah, the point is that all of these models rely on the possibility of saying that a given formula is true on the input, right? And if, so a logician may look at this theory of symbolic modeling and say, wait a minute, none of this commits to propositional logic. So propositional logic is just one, it's really the simplest of all logical formalisms. But in general, you could use different logical formalisms, and as long as you have a way of telling whether a formula is true on a given logical interpretation of that logic, then you'll be fine. You can use these symbolic models. And if propositional logic is not expressive enough to talk, in relational terms and say there exists a region in this image, blah, 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 then I can look for other logical formalisms. So if you want to express concepts in relational terms, one would say that the most natural choice is first-order logic. Yeah, indeed, there is a subfield of symbolic learning which is called inductive logic programming that is based on this logic. But we argue that there is a middleman between these two that represents a better trade-off between computational complexity and, let's say, expressive power. So modal logic is still able to express concepts in relational terms. You can say there exists something that has a given property. But, for example, the truth-checking algorithm for it is much more gentle in complexity terms. What is modal logic? Well, you consider a propositional logic, and you equip it with two new logical operators, which we call the diamond and box operator. So you can have formulas like diamond Q or diamond P and box Q. And instead of interpreting these objects on propositional interpretations, that is, mappings that assign true or false values to the propositions, we actually interpret them on graphs of such structures. So modal interpretations are so-called Kripke structures, which have a frame, which is essentially a directed graph, where each node is called a world, and the relation is called accessibility relation, so that you can say that a world 2, for example, is accessible from world 1. And each world, each node in this graph, has its own assignment of truth values to the propositions. Okay. So then the truth of a formula is relativized to a given world. For example, I can say that P is true on W1. I can say that P and Q is true on W2. And what about the two new logical connectives? Well, they act as sort of quantifiers across the accessible worlds. So if I say that diamond Q is true on W3, that's because there exists at least an accessible world where Q is true. In this case, W5 assigns true to Q. So diamond Q is true on the third world, W3. Conversely, with the box operator, you're not saying there exists a world, but you're saying every world that I see has a given property. So on W1 here, box P means every world that I see has a true value for P. So essentially, I am able now to express some form of quantification. Maybe I'll skip over this part, but yeah, you can use SoleLogics for checking modal formulas on Kripke structures. For example, here, what I did is I instantiated the example Kripke structures, and ultimately I am checking the truth of that formula on each of the worlds of the structure, and I find that it is true on 2 out of 5 worlds in the structure. So how does this help with the learning? This is very abstract. So so the key fact is that I can think of an image, in general, an image or a time series, as a Kripke structure where the worlds are regions or geometrical entities on my non-tabular object. So, for example, if I consider a time series, I can think of worlds as intervals in the time series, and for an image, I can consider rectangles in the image. But then I have to, I have to give a definition of propositions. What does it mean that something is? What can be true or false on a region in an image? Well, a region in an image and an interval in the time series, they essentially are an image and a time series, respectively. So I can do the same thing that people do when they extract features from an image, but I can do it in the specific worlds. So I can consider a set of propositions that are conditions on extracted scalar features. So I can compute, for example, the minimum of the I can say there's a lot of red. If I compute the minimum of the color red in this image within this specific rectangle, and yeah, so I can say that in this region there is a lot of red. Then I have to come up with a relation. What is the accessibility relation here? Well, if I'm thinking in terms of intervals, I can consider, for example, relations from interval algebra, or with rectangles, I can consider relations from region connection calculus, such as disconnected, externally connected, or partially overlapping. But again, I should choose one, so which one do I choose? Well, actually, I don't choose, because I can extend modal logic such that instead of having a single relation and 2 logical connectives, logical operators for it, I actually have a set of relations, and I have a diamond and a box operator for each of these relations. So this allows me, for example, to say that on an image, there exists globally a region with a lot of red, that is where the minimum of the color red is higher than a certain threshold. That is partially overlapping with a different region that has little green, and this latter region has a tangential proper part region with a lot of blue. And this is essentially a formula that I can translate in natural language. So then a symbolic learning dataset becomes a set of modal interpretations, that is Kripke structures, and each interpretation essentially has a frame, a graph, which may be, for example, a graph on intervals, in this case. the frame has many relations that allow me to navigate through the object, the image, or the time series. And each of the intervals have a set of pre-computed feature values. And so if I have an object such as this, I can then implement learning algorithms that extract symbolic models based on modal logic that can perform classification tasks on non-tabular data. So here, yeah, I have time to show you the fun part. So yeah, so I'm going to consider a public benchmark dataset for time series classification, and I'm going to show you what you can do if you train a decision tree based on modal logic on it. So this is a dataset with 360 instances, and each instance is a time series of 51 temporal points. And the task is that of gesture recognition. So the input variables, the input 24 variables are the XYZ coordinates of different parts of a person's arm while they perform some gestures. And the task is that of classifying the gesture as belonging to 1 out of 6 classes. Okay, so at a logical level, we can consider an interval-based frame. And for example, if we consider all of the intervals between 1 and 51, we get this number of intervals, which is pretty high. You could even, I mean, you don't necessarily have to consider all of the intervals. You may perform some pre-processing where you try to understand which intervals are the interesting ones. But at the moment, we are going to consider all of the intervals. And on each interval, you compute 24 features, which are essentially, I mean, in this case, I've chosen to compute the minimum of each of the 24 variables. So the neural networks perform well on this task. With the model decision tree, I achieve a 90% accuracy using a 10-fold cross-validation setting. But yeah, so let's see with the code what I can do. So first I import the packages, and I've trained the model using MLJ because model decision trees has an interface for MLJ. So I load the data set, and then I instantiate my model version of CART, which is this model decision tree, telling it to use relations from interval algebra. For example, partially overlapping, or later than, or during. So like I have an interval that is inside me. And I'm telling the model to use minimum as the feature extraction function on each of the intervals. So then I train the model on 10% of the data and test it on the remaining 90%. I achieve an 80% accuracy, but then the fun part is when I look at the model. So I can inspect the model and find that this tree has exactly 6 leaves, which essentially means that it has exactly 1 rule per class. So then with Sole, I can extract the rules, and actually, yeah, I can, so this, I'm not going to go into this, but basically this code is to show the, the purpose of this code is to show the rules together with the test metrics, for example, the confidence. So in the end, I get a set of 6 rules, 6 non-overlapping rules, and for each rule classifies the instances as belonging to a specific class. For example, the first rule has a confidence of 100%, which means that out of the 25 test instances, 25 instances were all correctly classified by this rule. And so here I can even translate these rules to natural language. This basically says there exists an interval where the x-coordinate of the left wrist is less than a certain threshold, and this partially overlaps with another interval where the hand tip, has a different property. I mean, a different position. And then, I mean, with this set, I noticed that 2 out of 6 rules basically have a low confidence. So in this case, these are 2 classes which kind of look the same because, yeah, it's all clear, not clear. Basically, it's the same gesture, except you are pointing upwards or downwards with your right thumb. So apparently, the model gets confused, and it cannot tell these 2 classes apart. Then, I mean, by means of very simple, I just compute the difference between the y-coordinate of the right thumb and the wrist. So basically, I can express the evolution through time of the orientation of the thumb. And if I retrain only using the samples from those 2 classes, then I get 2 rules which are a little bit more complex than earlier, but they have confidences of 83 and 95%. Yeah, and so the next step would be to translate this thing to natural language. And of course, this can be hard. In this specific case, I think this rule has a lot of redundancies. So one of the directions that we are going to deepen in the next months is the minimization of logical formulas so that you can reduce their size, or the approximation of logical formulas. And then we are also toggling with neurosymbolic solutions, and we are going to implement different algorithms for extracting decision trees or other kinds of models. So yeah, that concludes my talk. And if this was interesting, I mean, I hope this was interesting. Feel free to reach out if you're interested.
Thank you, Giovanni. I think we have time for one very short question. In the meantime, maybe the next speaker can come up. Yeah. Yes, please.
So you know the original CART algorithm. Well, it's a greedy routine that starts. You initialize the tree as a leaf, and then you test whether there is a condition that that splits the data set and minimizes. You minimize an objective, which is it can be some sort of entropy with respect to the classes. And at the model level, it's the same. Actually, it's difficult to explain, on the fly. But you essentially have a finite set of possible decisions, and you test each one of them, and you pick just the local optimum. And then you adopt that. Then you perform the split, and then you repeat on the children.
Thank you. Maybe one last very quick question. If not, let's thank Giovanni again.